Math 2414, integration by parts. Example 3. Integrate x squared e to the 2x dx. I want to remind you that the thing that suggests considering integration by parts is remembering that the word parts means parts of multiplication problems, aka factors. This is a product, it has factors. Integrate x squared times e to the 2x dx. All right, the hardest part again is getting it started, choosing what u equals and dv equals so that we can create the pieces needed to rewrite the expression as a difference. But when you're making these choices, there are things you should consider. Whatever you call dv, you need to be able to integrate to get the v. Well, I can integrate both of these. I might need to do a quick substitution when I integrate e to the 2x, but it is integrable. And then the other part is the u, which gets differentiated. I can take the derivative of both of these. But remember, we're trying to transform this to an integral that we can do. So let's think about what would happen if we decided to say that dv is equal to x squared. In other words, what if we said dv was the part we were going to integrate? If we integrated x squared, its power would go up to x cubed. And that would make this more congested than it is. So I don't think integrating the x squared is my plan of attack. Here's a little guideline. If you're doing integration by parts, and one of those parts is a polynomial, even just a monomial, a single term, I would always let that be the u. Why? The u gets differentiated, and when you differentiate a power, it gets lower. And with enough derivatives, it would eventually become a constant and not even be a variable anymore. So just as a general rule of thumb, if you're doing an integration by parts and one of those parts is a polynomial, let that be the u. And then hope that you can integrate the other part. So that being said, we're going to attack this by letting u equal to x squared and dv equal the rest, which is e to the 2x dx. Now before we jump into this, you might realize that there's going to be a problem even with this choice, which is the correct choice, by the way. When we define the u, we take its derivative to build the second integral, and we integrate the other part. Well, when you integrate an e, it stays an e. We'll have to balance out the 2x with the substitution. But when we differentiate the x squared, it becomes a 2x. And so when we put the du here, it's going to still have an x attached to an e, so we won't be out of the woods yet. But let's run with this and see what happens. If we choose u equal to x squared, then du is equal to 2x dx. That's not too bad. And v is going to be the integral of e to the 2x dx. Now be careful with this integral. It doesn't quite fit an integration rule. The integration rule that we would try to fit it to, of course, is the integral of e to the u du is equal to e to the u plus c. But along our guidelines of substitution, that doesn't fit the rule because it's a 2x and not a single letter. Actually, you know what? I'm going to change that rule slightly, and the only reason is we're already using the variable u, which, by the way, was a completely arbitrary choice of variable. It's just industry standard. I could have used m and n, dn. I could have used s and dt. I could use any two letters that aren't already spoken for in the problem. But since the u is already spoken for in what we have, it would be kind of bad to think of this in terms of u also. So why don't we change this to t? Or any other letter besides u or x, or e or d, or v. But I digress. If we're going to do this integral, we're trying to conform it to this rule, it would invoke a substitution. Now, if you need to manually do the substitution, do it, but this is going to become more the norm than the exception. You're in the middle of one integration technique, you have to pause and do another one. In this case, if we did a substitution here, we could say let t equal 2x, because t is in the place of the 2x here, then dt is equal to 2 dx, and if we solve that, I'm about to introduce a symbol I don't think I've introduced yet. It's a double-lined arrow. It's a symbol for the word implies. It's kind of like an equal sign that you can stick between equations. It would be wrong to put an equal sign here and write what happens next. but I will probably be writing that arrow often from this point forward, saying that this equation implies the following. If I multiplied both sides by a half, I would get 1/2 dt equals dx. Because remember, in the substitution techniques that I showed you, one of the moves was to solve for dx so that we can make the substitution here. All right, so if we make the substitutions, we get e to the t, because that's what t is representing, 2x. Dx is equal to 1/2 dt. The 1/2 being constant multiple, we can pull it out of the integral. Integral e to the t dt. And now it conforms to the rule, and we can finish integrating this. We have a 1/2. The integral of e to the t is e to the t, but remember the t was holding the place of 2x, so let's go ahead and unsubstitute it now. And we're going to hold off on writing plus a constant because we're building the expression on the right side of integration by parts, and we'll pick up the plus c at the end. So v is equal to this. I'm going to put a box around it because it's kind of hiding over here. By the way, it would be ideal if you could get to the point where you could integrate this instantly, even though it requires a substitution. Here's a little trick. If you're going to do a substitution, and everything is good except that missing constant, all you have to do to integrate is integrate like you normally would, but multiply by the reciprocal of that constant. In other words, multiply the reciprocal by the reciprocal of the derivative of whatever your substitution would be. If it's just a constant, the derivative of this is 2, its reciprocal is 1/2. It makes integrating some small substitution problems almost instant, but if you do it enough, you just start doing it anyway. All right, so we've got, let's put boxes around all the pieces. Here's u, here's dv, here's du, and then of course v is all the way over here. I'll put equals v. And let's do our integration by parts. So the integral of x squared e to the 2x dx is equal to u times v. So x squared times 1/2 e to the 2x. And in my opinion, the cleanest way to write that product is 1/2 x squared e to the 2x minus the integral of v, which is 1/2 e to the 2x, times du, which is 2x dx. All right, let's clean this up. The 1/2 x squared e to the 2x is just going to sit there for a moment. There's no double negative, so it stays a minus. But we have a 1/2 times 2, which cancel. And by the way, if they didn't, we could just figure out their product and even put it in front since it's a constant. And we're left with e to the 2x times x. But let's put the x in front, just because it looks better there. All right, so integration by parts has done its job so far. It's rearranged, it's transformed it from one integral to another, and I would argue that this integral is simpler than this one because the power on the x is gone, or rather it got lowered from 2 to 1. But we're not out of the woods yet, because this integral doesn't fit an integral rule. It would if the x wasn't there. So what do? And the answer is, treat this like its own problem and figure out how to attack it. Gee, I wonder what technique we can use to integrate this product, aka this thing with 2 parts. We're going to do integration by parts on here again. I'm going to introduce an abbreviation that's going to make perfect sense. IBP for integration by parts. In general, when you're integrating a product and half of that product is a polynomial like x squared, you may need to do integration by parts repeatedly until it becomes a constant. Because with integration by parts, you can set it up to get differentiated, and with enough derivatives, it would eventually be a constant. And if this were a constant, we could easily integrate e to the 2x. So now we got to do integration by parts again, and I'm kind of running out of room, but this one's going to go a little bit faster. Let's do integration by parts in red down here, just for that second integral. Integral of x e to the 2x dx equals. We're going to let u equal x, and we're going to let dv equal e to the 2x dx. I got to be careful, my v's and u's are starting to look alike. Du is going to be 1 dx, so that's good. Polynomial's gone, it's constant now. But for v, we would have to integrate e to the 2x, but we already did. We integrated it here, so the dv is going to be the same as, the v is going to be the same as before, 1/2 e to the 2x. Okay, let's see how this plays out. Integration by parts on this will give us u times v, so x times 1/2 e to the 2x, so 1/2 x e to the 2x, minus the integral of v du. So minus the integral of 1/2 e to the 2x times 1 dx, so it'll be the integral of 1/2 e to the 2x dx. It's getting a little crowded here, but I think I'm going to make it work. For this integral, the 1/2 is now a constant, we can pull it out. So we have this guy over here, 1/2 x e to the 2x minus 1/2 integral of e to the 2x dx. And for the third time in this problem, we need to integrate e to the 2x. We did it here, we did it here, finding v, and we're about to do it again, but we still know its results. Don't lose this piece over here, 1/2 x e to the 2x minus 1/2 times the integral of e to the 2x, but the integral of e to the 2x is still 1/2 e to the 2x. And this is our last integral, so it would pick up a plus c, but we'll import it into our final results up here. All right, so that part in red is done, but it's also in the way, so I'm just going to move it over here for a second. The integral of x e to the 2x dx was equal to, here's where it starts, after that last equal sign, 1/2 x e to the 2x minus, we get a half times a half is a fourth, e to the 2x. Now technically this should have a plus c because it's a standalone indefinite integral, but I just wanted to capture the results of integrating this guy by parts because we're going to have to take this answer and import it into that answer. And if you're thinking, whoa, this is getting out of control, I've got some news for you. This is just the tip of the iceberg, not just in this section, but for this entire class. All right, so let's clear this out of the way. And this is actually not that uncommon, not necessarily a problem with this issue, but the idea of working a problem, getting to a juncture and saying, you know what, I need to take this part of the problem out to the side, work it out, take its results, and put them back in the current problem. Do not be afraid to break a bigger problem down into a collection of smaller problems and then link them all together at the end. All right, we're almost done. All right, so we're back here. We've got this first part, this first term from the first time we did integration by parts, minus the answer to this integral, which is what we just did over there. The answer to that integral was 1/2 x e to the 2x minus 1/4 e to the 2x. And although it had a plus c over there as its own problem, in this problem we're just going to stick it at the end. And there's really not much to clean up. It looks like there are some like terms, but there are not. Really the only thing we should do is distribute this negative, which will keep this term negative, but make this one positive. But if you want to push it one small step further, all of these have e to the 2x as a common factor. So I'm going to do two things to get this final answer. Number one is distribute the negative, and remember this will become a plus. But at the same time, I'm going to factor out their common factor of e to the 2x. That would leave 1/2 x squared minus 1/2 x. And remember, this will become positive upon distributing the negative sign, positive 1/4. And I think that's the best looking answer because our original integrand was a polynomial times e to the 2x, and our antiderivative is a polynomial times e to the 2x. One more quick comment. If you really wanted to be cute, you could factor a 1/4 out. This is totally optional, but I've seen some professors say this is a better looking answer. If I factor a 1/4 out, and factoring out fractions is not in everybody's comfort zone, but you would get 2x squared minus 2x plus 1 times e to the 2x plus c. And if you're wondering why do these become 2's, because this 1/2 is the same as 2/4. So if you have 2/4 and factor out the 1/4, you're left with 2. And I think this would probably be considered the best looking answer because the polynomial no longer has rational coefficients. Well, they're rational, but they now have integer coefficients, I should say. But in terms of my class, I would probably want this answer, and if this were a test question, I would put something in the instructions that say, be sure to factor e to the 2x out of your final answer. All right, so that one was crazy, and I wish I could tell you that's as crazy as it gets, but you're just on the precipice of Calculus 2. It's going to get worse.